we have started to learn about a very powerful method of a scattering problem, and that was actually the partial wave analysis method or method of partial waves. You have learned how to deal with the problem of a scattering for finding the differential scattering cross section and the total scattering cross section by method of partial waves. Now today we are going to start the application part of this theory, and as the first example of its application we are going to see a scattering from a hard sphere or rigid sphere. Actually, this is a very most important application of partial wave analysis, and in examination this question is asked uh, several times, and this question in fact when asked contains three parts. First of all, you have to obtain the expression for the phase shift for a perfectly rigid sphere which is represented by this particular potential. Okay, and after that you have to discuss to find the total scattering cross section in two cases, in two energy limits. The first one is low energy limit and another will be the high energy limit. So actually all these three aspects we will discuss in this lecture. First of all, we will see the expression for the phase shift for a perfectly hard sphere or rigid sphere, and after that you will see how to calculate the total scattering cross section in two energy limits. In fact, as I have explained Bessel function in my previous lecture, and now in this lecture too you will find the use of the Bessel function and the spherical Bessel function. So I will suggest you, if you have not a concrete knowledge of Bessel function and spherical Bessel function particularly, then go through my previous video on this subject, both in quantum mechanics in this chapter and also in mathematical physics. Because when you have a concrete knowledge of Bessel function, then you will be able to understand this type of lecture. Okay. So now let us start to deal with the problem of a scattering from a hard sphere or rigid sphere. In fact, when you talk about a perfectly rigid sphere, let us say of radius a, in quantum mechanics, we represent this rigid sphere by a potential function which is defined like this. If r is the distance of the test point, or you can say point of observation from the center of the sphere, and there may be two situations. First one will be if this is your sphere, its radius is a, and there is the observation point P here at a distance r, or it may be here which is outside of this sphere. So there will be actually two situations. So if potential is infinity, when you talk about a point inside the sphere, that is r less than a, and this potential vanishes, this potential abruptly fall to zero when we talk about the region where r is greater than a. So this is actually the quantum mechanical description of this rigid sphere. In case of rigid sphere, you say rigid sphere, but you can say that this is a spherically symmetric potential, and this potential is defined like this. V of r is infinity when r is less than a, and it is 0 when r is greater than a, where a is the radius of this sphere. Okay. Now you can see since v of r is plus infinity at the boundary and inside this sphere, so definitely in this region there will be no chance of existing the incident particle. When a beam of particle will strike such a potential, the particle will not penetrate into this sphere. So this sphere is called hard sphere or rigid sphere. It means there will be no penetration of the particle inside the sphere. And if the particle is not inside the sphere, then definitely the probability of finding of these particles inside the sphere will be 0. And according to Max Born interpretation, if probability of finding of particle inside this sphere is 0, what does it mean? It means the wave function will be 0 inside the sphere. So you can say that the wave function vanishes for the region where r is less than a. Okay. Now, as you know, in partial wave analysis, we always solve the problem in terms of the radial part of the Schrodinger wave equation. Okay. So now let us write the radial part of Schrodinger wave equation for the region where r is greater than a, because in this region you can see that potential is 0. So we will write the radial part of Schrodinger equation in this region r equal to greater than a. That is, if you are talking about the region where potential V of r is 0. You know, if V of r is 0, then this radial part of Schrodinger wave equation will be what? This will be 1 over r squared d dr, r squared d dr minus L times L plus 1 over r square plus 2 mu e over h bar square UL of r equal to 0. Okay. Here actually this UL of r is the wave function. Okay. This is the well-known equation, so I am not interpreting this result because you have learned these things several times in quantum mechanics. Okay. Now, actually, to set this equation into a convenient form or into a standard, into the form of a standard differential equation, so we will be able to seek its solution. Let us make a substitution. We introduce a new variable rho, and this rho is defined as this is equal to k times r, or you may say that this r is equal to rho over k, where k is a constant, you know, and this k is actually what? This k is actually equal to root over 2 mu e over h bar square. Okay. Now, when you will substitute rho equal to kr or r equal to rho by k in this equation, that is the radial part of the Schrodinger equation, then this equation will reduce like this. I have not done all the steps of the algebra. You can do it. So this will be d rho operated on rho square d ul by d rho plus rho square minus L times L plus 1 UL of rho equal to 0. Okay. Now further we substitute this wave function UL of rho in this form, that this is VL of rho divided by square root of rho. Okay. So when we will substitute VL of rho over square root of rho instead of this UL of rho, then this equation 1 becomes like this. You can check it. Substitute instead of UL of rho, VL of rho over square root of rho, and then you will see that this equation becomes, as you can see in this equation 3. Now, when you will observe this equation 3, and if you have studied Bessel function or Bessel equation, differential equation, then you can easily say that this equation 3 is nothing. This is simply the Bessel's equation of order L plus half. Okay. And you know, if it is the Bessel equation of order L plus half, its general solution will be just a linear combination of the Bessel function capital J L plus half of rho and the Newman's function, which is also called Bessel's function of second kind, n L plus half of rho. Okay. if you will take the linear combination of this JL plus half and NL plus half, then you will get the general solution of this Bessel equation defined in equation 3. Okay. In fact, the solution NL plus half is not satisfactory because it diverges at rho equal to 0, and therefore the solution of equation 3 is expected like this. This is VL equal to a square root of pi over 2 times JL plus half of rho. It means in this you can see, since this NL plus half of rho diverges, it becomes diverges at rho equal to 0. So to get a finite solution, we simply say that the solution of this equation 3 will be simply the Bessel function of first kind, that is JL plus half. Okay, we neglect N plus half, NL plus half. Here actually I have multiplied this Bessel function JL plus half by this constant factor a square root of pi by 2. Actually, you know, this square root of pi by 2 is a constant which has been chosen for convenience, and it does not affect the solution of the problem. Okay, this is just a constant factor, but it makes our calculation very convenient, very suitable, and therefore for convenience this constant factor has been taken. Okay. Now, if you have defined VL, but in our the original equation, you know, is in terms of UL, and you have related this UL with VL by this relation, so you can now obtain the value of this UL of rho. We have actually assumed that UL of rho is equal to VL of rho over square root of rho. So now the solution of this equation defined in equation number 1 can be written like this. This is a square root of pi over 2 JL plus half of rho over a square root of rho. Okay. But actually, when you talk about this UL of rho, what is this? In fact, this is simply the spherical Bessel function. So UL of rho is recognized as the spherical Bessel function a small JL of rho. Okay. So you can also say that this small JL of rho is equal to pi over 2 rho, square root of pi over 2 rho times capital JL plus half. Actually here this small JL, you know, this spherical Bessel function is represented by a small j, and the ordinary Bessel function is represented by this capital J. So the spherical Bessel function JL of rho is equal to a square root of pi over 2 rho times capital JL plus half of rho. Okay. And you know how the spherical Newman function is defined? This is related to the spherical Bessel function JL of rho by this relation. NL of rho, this is equal to minus 1 raised to the power L plus 1 times JL of rho. Okay. But you have already obtained the value of this JL of rho here. So let us substitute it in this equation. So NL of rho is equal to minus 1 raised to the power L plus 1 times a square root of pi over 2 rho times JL plus half of rho. Okay. So we have defined or we have related the spherical Bessel function JL of rho with the ordinary Bessel function JL plus half of rho, and this spherical Newman function NL of rho. Okay. So as we have stated earlier that actually the solution of this equation 1 will be just a linear combination of the Bessel functions JL and in fact NL. So now the general solution of equation 1 can be expressed in this manner. UL of rho equal to A times JL of rho plus B times NL of rho. You know, actually this A and B are constants, arbitrary constants, or you can say these are actually the integration constants, which are evaluated by using the appropriate boundary conditions. Okay. Now let us take this A is equal to C times cos delta and B is equal to minus C times sin delta. Okay. Actually, you will see later on that this delta AL is actually the phase shift due to the potential. Okay. But till now I am not telling that this is phase shift, but in the in course of our discussion, this fact will come to our in the picture that delta L is nothing. This is actually the phase shift. And as our aim is to find the expression for phase shift first of all, so you will see our aim is to find the expression for this delta L. So when you substitute C cosine of delta L for A and minus C sine delta L for B, then what will be this equation number 6? You can see this equation will become UL is equal to C cos delta L times JL of rho minus C sine delta L times NL of rho. Okay? You can take this C as a common factor, and instead of rho, now let us substitute K times R. So in this condition, you can say that this UL is a function of R because K is constant, so I have written only R. Okay, you can also write KR. And this will be C times JL of KR times cosine of delta L minus NL of KR times sine of delta L. Okay. In fact, this equation which we have obtained in equation number 7 represent the solution of the wave equation for R greater than A. R greater than A. Okay. Where wave function does not vanish. But you know, at the boundary, that is at R equal to A and for the region R less than A, this wave function just vanishes. It is zero because potential is infinite. And therefore you can use this boundary condition that this function vanishes at this R equal to A. So you can use the boundary condition UL of R is equal to 0 at R equal to A. Okay. Now let us use this boundary condition in this equation number 7. So when you will take R equal to 0 in RHS of equation 7, you must have to take this UL equal to 0 in LHS. So you can see this equation after imposing this condition becomes 0 equal to C times JL of KA because R is equal to A. So I have replaced this R by A times cos delta L minus NL of KA times sine delta L. Okay. And as this constant C cannot be 0 because if C is 0, then both A and B will be 0. And if both A and B are 0, then UL will be 0. It means particle is nowhere, but that is not a real physical situation. Particle is present outside of the sphere because we have incident the particle on this potential. Okay. So physical situation says that this constant C can't be 0. So if C is not 0, definitely the factor inside this square bracket will be 0. And if you will take that factor is square inside the square bracket 0, then you can see this that will simplified as tan delta L is equal to JL of KA divided by NL of A. You can see. tan delta L will be equal to JL of Ka divided by NL of K. Actually, this is a very important result, or you can say that this is the expression for the phase shift which is produced by the spherical potential which we have defined. Okay. So this equation gives the phase shift delta L of the Lth partial wave. This is the phase shift of Lth partial wave. Okay. Now from this equation you can obtain a very important relation for sine square delta L. How you can obtain? You will have to do simple trigonometry. If you know tan delta L, you can say we can find sec square delta L. How? This will be equal to 1 plus tan square delta L. And sec square delta L, it means this is 1 over cos square delta L. So you can obtain from here cos square delta L. And once you know the value of cos square delta L, it is easy to find sine square delta L. This will be equal to 1 minus cos square delta. But I have not done this elementary mathematics here. When you will try, you will see that this sine square delta L will be equal to this. This is JL square over JL square plus NL square. Okay. This is actually a most important result because you know in a scattering problem, whenever you write the expression for the scattering cross section, this factor sine square delta comes in that. Therefore, I have obtained here the value of sine square delta L and already. Now, after obtaining the value of this sine square delta L, you can define the scattering cross section for the Lth partial wave. And for this, you have to remember the final result for the scattering cross section of our previous video. You have seen that the total scattering cross section is defined as 4 pi over k square times summation over 2l plus 1 sine square delta L. Okay. But here we are talking about only the Lth partial wave. So I have dropped the sign of summation. So if your aim is to find the scattering cross section only for Lth wave, then there would be only one wave, and so there is no sign of summation. So sigma L, which represents the scattering cross section for Lth partial wave, that will be given as 4 pi over k square times 2l plus 1 times sine square delta. But as we have already obtained the value of this sine square delta L here, so you can see this is 4 pi times 2l plus 1 over k square times jl square over jl square plus nl square. Okay. And you can see actually the value of this sigma L depends on the quantum number L. So for different L, a scattering cross section will be something different. Okay. Now, if you want to find the total scattering cross section, how you can find it? You have to take this sigma as 4 pi over k square, okay, summation 2l plus 1 times sine square delta L. This is the well-known expression for the total scattering cross section. But you have seen that this sine square delta L is equal to this much. So the total scattering cross section is given by this result. Okay. So in this way, you can obtain the total scattering cross section. Now, from this equation, you can see the cross section at all energies may be evaluated. Okay. But we will discuss here the two limiting cases, and those two limiting cases are actually the most important cases. First one is the low energy limit case. It means we will calculate the total scattering cross section in case of the low energy limit, and after that we will talk about the calculation of total scattering cross section for the high energy limit. Okay, so now let us first of all talk about the total uh, calculation of total scattering cross section for low energy limit. In fact, when you talk about the low energy limit, what does it mean? It means this implies the domain of K for which this Ka is much smaller than 1. Energy is much smaller, and you know that this K is a square root of 2 mu E over h bar square. So when this E will be very small, then this Ka will be much smaller than 1. So in this limiting condition, we have to use this limit that Ka is much smaller than 1. Now, first of all, I am defining the value of the spherical Bessel function JL of rho and Newman function JL of rho in the limiting condition when rho tends to 0. Actually, I have written this result directly because it is the subject matter of your course on mathematical physics on Bessel function, and there you will get it. For that you have to watch my videos on mathematical physics. And let us see, this result is limit rho tends to 0 JL of rho equal to rho to the power L over 12 plus 1 factorial, and limit rho tends to 0 NL of rho, this is 2L minus 1 factorial over rho to the power L plus 1. Okay. Actually, when you write these results are consistent with low energy. When energy is low, only then these results are consistent. Okay. And in this condition, only few of the angular momenta contribute. Okay. In fact, if these relations show that the energy is these results are consistent in low energy limit, and the value of delta L decreases rapidly with decrease in L. Okay, with increase in L, and consequently the scattering is prominently due to S wave. Okay, the scattering is mainly due to S wave. When you talk about S wave, that means the wave for which L is equal to 0. So mainly in this case, a scattering takes place due to the wave for which L is equal to 0. Okay. Now, as you have seen, the result for the phase shift tan delta L equal to JL of Ka over NL of Ka. But you know that this JL of Ka, it is related to the Bessel function capital JL plus half by this relation. You have already seen earlier. This is a square root of pi over 2 Ka times capital JL plus half of Ka. And NL of Ka, this is minus 1 raised to the power L plus 1 times a square root of pi over 2 Ka times J minus L minus half of K. Okay. Now you can see this factor and this factor will cancel out, and therefore this tan delta L, this will be equal to what? This will be JL plus half of Ka over minus 1 to the power L plus 1 times J minus L minus half of K. But as I have told you that in this condition, the scattering is prominently due to S wave. That is the wave for which L is equal to 0. So definitely we have to calculate the phase shift for the S wave. And for getting it, you have to put L equal to 0 in this above result. So tan delta L will be now written as tan delta 0. Here 0 stands for L. And JL plus half. L is 0. So this will be simply J half of K and divided by minus 1 to the power L plus 1. But L is 0. So this is minus 1 to the power 1, which will be minus 1. So there is minus sign here, you can see. And J, L becomes 0. So this is J minus half over K. But you know that this Bessel function J half of Ka, this is defined as a square root of 2 over pi Ka times sine Ka, and J minus half of Ka, this is equal to a square root of 2 pi Ka times cos Ka. So this and this will cancel out, and you can see tan delta 0 will be equal to minus tan Ka, and therefore delta 0 is equal to minus Ka. So in this condition, you can see for S wave, the phase shift is equal to minus Ka. Now after getting the value of phase shift delta naught, which is equal to minus Ka, now we can obtain the total scattering cross section for low energy limit. In case of low energy limit, you must take L equal to 0. Okay, and you have seen earlier in this here that the expression for the total scattering cross section is this much. Okay, this much, or you can say this much. Okay, now taking L equal to 0, we can obtain the total scattering cross section in this case, sigma equal to 4 pi over K square summation 2L plus 1 times sine square delta L. Okay, but you have to take L equal to 0. So when you will take L equal to 0, this 2L plus 1 will be 1, and therefore this is simply equal to 4 pi over K square times sine square delta naught. Instead of delta L, you have to write delta naught because L is 0. But you have seen that this delta is equal to minus K. So sine delta naught will be equal to minus sine K, and when you will square it, minus sign will vanish, and this will be 4 pi over K square times sine square K. Okay, but this result holds when Ka is much smaller than 1. Energy is very low. And you know, if angle is very small, limit theta tends to 0, sine theta is equal to theta. So under this limiting condition, sine Ka will be equal to Ka. Okay, and sine square Ka will be equal to Ka whole square. Therefore, in this limiting condition, under the low limit energy limit condition, you can say that this will be equal to 4 pi over K square times Ka whole square. And this is simply equal to 4 pi A square. So the total scattering cross section is equal to 4 pi A square. This is a most important result. In examination, sometimes this result will be written and you will have to prove it. Okay. But you know, if our sphere is of radius A, what will be its geometrical cross section? The geometrical cross section of a sphere of radius A is simply pi A square. pi a square is the geometrical cross section. Okay, and the geometrical cross sectional area is equal to the classical value of the cross section. So you can say, actually, if we are talking about a sphere of radius a, then in terms of classical mechanics, the scattering cross section should be pi a square. Okay, but here you can see the scattering cross section what we have obtained by quantum mechanical approach, that is not pi a square but 4 pi a square. So you can say that the quantum mechanical result for this cross section is just 4 times of the classical expression for the same radius. Okay. So we conclude that for low energy particles, the cross section is 4 times of the geometrical cross section of the rigid sphere. Okay, because pi a square is the geometrical cross section. Okay, I think you have clearly understand this calculation. This is a very interesting fact. Okay. Now, after getting the idea of low energy limit for the calculation of total scattering cross section, now let us see how we can find the total scattering cross section in the high energy limit. Okay. So here situation will be just reverse. When you have talked about the low energy limit condition, you have taken the condition Ka is much less than 1. But if you are now talking about the high energy limit condition, the condition will be just reverse, that this is the case of Ka much greater than 1. So for high energy limit, this Ka will be much greater than 1. Okay, for a given value of L or fixed value of L. Now, when you will substitute the asymptotic form of the spherical Bessel function small jl and nl in our original equation A, which we have obtained for the phase shift, you can see we have obtained here sine squared delta L. When you will put the value of JL and NL in asymptotic form, I hope you can remember the asymptotic form expression for JL and NL, because I have already discussed in my previous video, so you can get that thing in that video. So when you will actually use that, you will find that sine squared delta L is equal to sine square K. Under the condition L is much smaller than Ka. Okay, L is much smaller than K. In fact, this result indicates that the phase shift oscillates rapidly between 0 and 2 pi, because this is sine function, and the sine function sine square theta will be 0, that is it is minimum when theta is 0, and in a spherical polar coordinate system the theta coordinate varies between 0 and pi. Okay, so assuming that only these waves contribute to the partial waves for which L equal to 0 to L equal to Ka, then the total scattering cross section will be what? Sigma बराबर 4 pi over K square summation L 0 to Ka at times 2L plus 1 times sine square K. So when you will actually sum up this series, you will get that this will be 4 pi over K square, and the summation L 0 to Ka 12 plus 1 sine square Ka. In fact, what will be this summation? 2L plus 1. 12 plus 1. This will be, when L will be 0, this will be 1, plus when L is 1, then this will be 3. when L is equal to what? 2. L equal to 2, then this is 5. So this is just the sum of the odd numbers. And finally you will put this Ka. Okay. In fact, at times sine square Ka. Actually this sum will be equal to 4 pi over K square times K square A square times sine square Ka. Here K square and K square will cancel out and your result is almost 4 pi A square sine square K. As I've told you that this sine square Ka is an oscillatory function. It oscillates between 0 and 1 because the minimum value of sine square Ka will be 0 and its maximum value will be 1. Okay. So this cross section has not a fixed value, but it oscillates between 0 and 4 pi A square. When sine square Ka is 0, sigma will be 0. When sine square Ka is 1, then sigma is 4 pi square. So the minimum value of sigma minimum is equal to 0 and sigma maximum, this will be equal to 4 pi A square. And between these two limits, the value of this cross section oscillates. It is of oscillatory nature. Okay. Therefore, definitely in an experiment, in an observation, we do not observe this oscillation because this is a very rapid variation. We only observe the average or mean value of this. So in fact, the observed value of total cross section will be the mean value of this 4 pi square sine square. 4 pi A square is a constant factor. So for getting the observed value of a scattering cross section, you have to take the average value of sine square Ka. And you know average value of sine square Ka is what? This is 1 over 2. This is simply 0 plus 1 over 2, that is 1 over 2. Therefore, the observed value of a scattering cross section in this case is sigma equal to 2 pi A square. 2 pi A square. When you have seen this result, we have definitely been get surprised because in case of low energy limit, sigma was 4 pi A square. It was not of oscillatory nature, but in case of high energy limit, sigma is of oscillatory nature. It varies between 0 and 4 pi A square, but its observed value is 2 pi A square. This is just like alternating voltage. Alternating voltage varies, but when you measure it by a meter, by a multimeter, the reading is not variable. It gives a proper value. That is actually the RMS value, no? So this is actually the observed value or the measured value, which is 2 pi A square. Okay. But why this result comes like this? You can see I have mentioned it here. Thus we see that in high energy limit, the scattering cross section is twice the geometrical cross section. Again you can say that pi A square is the geometrical cross section, but here the observed value of a scattering cross section is 2 pi A square, so it is 2 times of the geometrical cross section. Why this result is like this? Actually the reason for this anomalous result is the shadow scattering. Shadow scattering is the reason behind this anomalous result. In fact, when you talk about the finite value of Ka, then diffraction takes place around the sphere in the forward direction. Okay. And therefore the total measured cross section is nearly 2 pi A square. Okay. So I think this session was definitely very interesting for you, and this is a very important concept, and it is most important concept for your examination purpose. And I hope you have clearly understand each and every aspect of my video, and definitely you have enjoyed. So thank you very much.